Okay, so today we're going to be doing this AP Physics C FRQ. So I'll just start right away. I'm going to just sort of go through how I would go through reading it. A long track inclined at angle theta to the horizontal, right? To the horizontal. Okay. Has small speed bumps on it. So boom, 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 speed bumps, right? The bumps are evenly spaced at a distance d. So from bump to bump, it's d. This is d. This is d. Okay. The track is actually much longer than shown with over 100 bumps. So we have 2, 4, 6, 8, 10 bumps. There's 10 times longer, at least. A cart of mass m is released from rest. Cart of mass m is released from rest, which, first of all, this means that VI is equal to 0. A student notices that after reaching the 40th bump, the cart, okay, I already know this is not going to be. The cart's average speed between successive bumps no longer increases. So you're in the first law right here. You're in Newton's first law. No longer increases. You're at constant maximum value of V average. So this part right here is Newton's first law. Okay. Consider the cart's motion between bump 41 and 44. In the figure below, sketch a graph of the cart's velocity v as a function of time from the moment it reaches 41 until the moment it reaches 44. Well, it says that after 40 there is a constant velocity, right? There's no acceleration. But at each bump, you're going to abruptly decelerate, right? Which means that you're going to be constant, but you're going to be constantly abruptly decelerating, right? So let's draw how this would look. We're just going to assume rest is, let's say, right here. Let's just say, I'll just go somewhere else. So I'm going to go like this, abruptly drop. Oh no, I forgot it does that. Abruptly stop, then constantly accelerate up to here. Then we're going to abruptly go down again, constantly accelerate. You notice how I'm making each point leveled, the most leveled I could make it. We're going to go down abruptly. These actually, maybe I should make them a little more abruptly. Okay, let's start here. Boom, and then accelerate, and then boom, and then accelerate, and then boom, and then accelerate, and then boom, right? So this should be up here because I am trying to draw to scale. Obviously it's not going to be exact, but the people that are grading this need to understand that you have an idea of what's going on. So this is sort of an idea of what the graph would look like. Everything here, this is abrupt deceleration. This is when they're hitting the bumps. You could specify to show that you know what you're doing by just going abrupt. Okay, and this is your constant velocity here with no increase. Then it says, over the same time interval, draw a dashed horizontal line at v equals v average. So they're basically saying sketch the velocity. And they're telling you dashed horizontal, which literally tells you it's constant velocity, which means it's not going to look like this with dashes. It's not going to look like that. It's not going to look like this. It's going to be dashed horizontal line. Let's go. Just say, again, this is not drawn to scale, but I'm going to try my hardest. Yeah. These should all be leveled. It's just harder with this pencil. Okay. This is what your graph would look like. You notice that everything here is aligned as it should be because they are in the same velocity. Okay. Suppose that the distance between the bumps increased but everything else stays the same. Is the maximum speed of the cart now greater than, less than, or the same as it was with the bumps closer together? You may think this is such a dumb question. It's pretty like evident, but you have to be able to explain your reasoning. So they're telling us that right here, the distance is increasing. So let's say this is the distance from one bump to one bump. Now the distance from one bump to one bump, let's say, is D. So it asks, is the maximum speed of the cart greater than or less than? Well, it's going to be greater than, right? Because when you think of it, the cart's going to have more room to accelerate with more distance. Because when you think of just in general the relationship between distance and acceleration, they're related to each other. They're proportional to each other. Okay, so I'm going to just check off this greater than. And they're saying to briefly explain. They don't specify quantitatively, qualitatively. You could do both. You could probably better to justify it both just to show. But either way, you're going to get the points if you do it correctly. So to use a qualitative method, you could just explain that with more distance, you have more room to accelerate. But you could also say that when we look at a formula, we have to consider a formula with velocity, acceleration, and distance. No time. So it's going to be this formula, Vf squared equals Vi squared plus 2Ax. Delta x, it's the same thing. Now, our Vi squared is 0 because, like we said here, Vi is equal to 0. So this cancels out. Our 2 is a constant, so we can just ignore it for right now. So we have a Vf squared is equal to A delta x, which means that we can assume our Vf squared is proportional, not directly as in 1-to-1 ratio, but proportional. We'll use this, proportional to our distance. This would be your quantitative reasoning. Okay, would the bumps return to the original spacing, so back when the distance between one and one is D, the track is tilted to a greater ramp angle of theta. So they're making the track from, let's say, here to like that. That's not a good representation. They're making it from this to like that, right? They're just increasing theta. Is the maximum speed now greater than, less than, or the same? Okay, so again, this is one of the questions you're probably going to look at and be like, oh, this is really stupid, but it is. It's greater than, right? Because it's more steep, it's accelerating quicker. But you have to be able to explain this. So mark off our greater than. Check. Okay. To briefly explain, there's so many approaches you can take here. Let's just think of it. I'm going to use like a quantitative reasoning, and then I'll explain it qualitatively. Okay, so we're looking at theta. We're not looking at time. We're looking at acceleration. We're looking at distance. We're looking at everything that can change. So I'm going to go again. Use this Vf squared equals Vi squared is 2A delta x. Remember, Vi is constant. Our 2A is going to be constant now, because it remains the same. This is why, let me explain why this is constant. This is constant because it's not changing. So Vf squared alongside this, this is equal to 2A delta x. So if your acceleration is increasing, your final velocity is going to also increase. They're proportional, right? Okay. Now to look at it another way, we can think of, sorry, that was my chair, through unit 2. So we know that we're in Newton's second law because there's acceleration, right? It's accelerating when you increase the angle. So we know that F net is equal to mass times acceleration. And when we think of this, we have to think of what it really looks like when you're increasing the angle, right? So let's say this is my original angle and theta, right? And here's my box. Boom, boom, boom. And then it goes boom, right? And I'm gonna do this one with red so everybody can see. One, oh my god. Just come on, man. 1, 2. This is not working the way I thought it would. 2. You can see, this is my FG parallel, right? FG parallel. Okay. Now let's look at it when our theta is increased. So make the angle a little bigger. Boom. 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 Okay. Go with that. Now theta is increased. So same box. Pretend whatever. Okay, so here's our force of gravity, right? Through the middle. But now here's our Jesus. Why is it doing that? Okay. Force of gravity is supposed to be right down the middle, so I'm gonna like just redo this myself. Boom, 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 boom. You can see that the FG parallel is gonna increase, right? You can see that when you increase theta, you're increasing your FG parallel. I'm really focused on here. I should have just did that. Okay. So that is another way to. Now, okay. So based off this, you look at this formula. So this means that our FG parallel, we know that our FG parallel is a set formula. It's equal to mg sine of theta, right? So mg sine of theta. Our mg is going to be constant, right? Sine has a set value. Sine doesn't change based on the equation. So it means that our FG parallel is proportional to theta. Right? Okay. So theta and g, I'm going to just show you guys something also. When I say this is constant, it doesn't mean that you can completely eradicate this. It just means that when I'm comparing it, it's not going to change. But let's say I want to account for the g. I'm going to say, this is constant, right? Let's just say g sine theta. Sine's not going to change. It's only going to change based on this. So these depend on each other, right? The value of this whole thing depends on theta, because theta will change sine, and obviously these constants, but in general. Okay. FG parallel is going to be proportional to theta and to the acceleration. Gravity is equal to, the g is equal to acceleration, not that gravity is equal to acceleration all the time. Okay, so FG parallel is proportional to the theta, because as you change theta, you're changing this. If I make theta 30 degrees versus 20 degrees, my answer is gonna be smaller. That's the idea behind this.